team, thank you so much for joining us this evening. I'm Maddie. This is Science Side Up. And tonight I have Jordan from Reason to Doubt co-hosting. You want to say hi, Jordan?
Hey, how's it going? Thanks for having me. This is like my favorite thing.
I'm so excited for tonight, and I'm so excited to have you here for tonight. Because amongst the science friends, you are you bothered to sit down and do some of the math of the heat problem.
Yeah, I tried to cheap out the first time I did it, and then George did his numbers, and I guess I had to be rigorous the second time. But it's fun. I mean, math is fun.
Math is very fun. I got a whole degree in it, and I appreciate you doing that work. So part of that, I'm so excited about this video because this is team standings. Like they're gonna do math according to the title, right?
Okay.
So,
that could be good. Could be.
I'm nervous. I'm nervous for them. So this is NOAA's global flood heat issue resolved. Math reviled?
Does that mean like they revile the concept of doing math?
I don't know. I think one of the questions here is that a typo? Right? Like, is it supposed to be revealed? Was it supposed to be the math revealed?
Revealed, maybe, or maybe like the reviling our evil atheist math. I don't know.
I don't know. So I'm very just saw the title of this and I got really excited. So
this is on Raw Matt's channel?
Yes, this is on Raw Matt's channel, which is now titled Young Earth Creation. Not even Young Earth Creationism, right? But I don't know. Okay, so I vote we get into this because you are being amazing and are missing part of your D&D game for this tonight. So
just the first part.
Okay. Oh, and by the way, everybody, all of Jordan's links are in the description. If you don't follow him, you should do that. And I was a good host, and I put links in the description.
I do appreciate that. Yeah.
Yeah. Okay. Well, let's get started with this. I'm very excited. Okay.
Okay.
So hi, Erica. Yeah. That was just part of the intro. Dr. Jackson. So much music. Okay. I haven't watched this beforehand because I want you guys to get my just raw reactions. Okay.
I'm 90% sure I haven't seen it either.
I will give Ramat this. His videos are better edited than mine.
What does Ramat do? Is this what he just does?
For all those who
I have no idea
the work that we're doing here on Standing for Truth, please hit that subscribe button because we are just getting started.
Those graphics.
My name is Maarten, and I will tell you something about heat during the flood. Is heat a problem or an answer?
Oh,
there are many flood models available, but they all...
Okay, who is this guy?
So when they did, George Bond did a refutation of my math, a refutation in big air quotes.
Okay.
And as part of that, they referred this guy. I don't know if they referred to this video, but they showed a clip, and I remember his voice. He had a very unique speaking pattern.
Okay.
Cool. All right.
Okay. And just, I got so excited, I forgot to say this at the beginning, team. For you guys that don't know, the heat problem is, if Noah's flood happened, right, then the energy of that event, right, and of, depending on, what other things are trying to be, accounted for with the flood by young Earth creationists, squeezing billions of years of radioactive decay into, 12 days or however long, into less than a year. All of that, the energy to move the continent of Australia at race car speeds, right?
They have to form every stage of the continents, but one right after the other, like a slideshow.
Yeah. Rapid movement of continents, all this thing that younger creationism claims has to have happened. Well, that produces enough heat to melt the Earth several times over. And some people like to say that that's somehow not a problem. That sounds interesting.
I mean,
So,
according to the professional creationists, it's a problem so large that the only solution is miracles. Like Baumgartner straight up says that the only solution to this problem is to invoke a miracle from God. There's no natural solution.
Okay.
Full stop. Standing for Truth disagrees.
All right. So let's hear their like statement. Let's hear them set up the problem for us.
All have one problem in common. They have too much heat involved. And take a look at this statement. A sudden exposure of the mantle to 70% of the Earth's surface would release enough heat energy to boil the oceans dry several times. This is comparable to the statement, your oven has enough energy to set your curtains on fire. They are not on fire, so you don't have an oven.
No.
I mean, if you were in the hypothetical where like that heat is staying down in the mantle, sure, but like that's not what they're saying, right? That I assume that he's going to talk about how the crust is going to get vaporized and stuff. So yeah, that's more like saying you put your curtains in the oven, you know, but it'll be fine.
Right. Okay.
For comparison, the Tsar Bomba released more energy than all weapons and bombs in all wars combined, yet nobody got killed. So two things are important.
Wait, do you know what the Tsar Bomba is?
I think, and I could be wrong, but I think that was a weapon set off by the Russians as like a test, so it wasn't used in combat.
Oh, okay.
So it was like a huge explosion, but it was not against any particular target. I think. I could be wrong.
Okay. Yeah, I mean, like, okay, so you know, that could be, you know, a great, I think maybe another reference would be the United States tested nuclear weapons in New Mexico, right? And they did them far off on the desert, away from people, and that didn't kill anyone, right? But the United States also dropped bombs on populated areas.
Which did kill people.
Which did kill lots of people, so it turns out.
I guess what he's saying, what he's trying to say is having heat.
Sorry, largest bomb ever, 57 megatons.
Cool. Having heat isn't a problem. It's a matter of where the heat is, which I guess is true.
Which I guess
as far as it goes.
Right.
The problem is that the heat is in the crust, where like Noah and all the little animals are. So.
Right, and for this, you know, for this like Noah's flood, that's a good question. How many times tonight? You guys can start taking bets. How many times will you get me to say, "Oh, sweetie, no"? You know, like if the flood is in fact global, then all of that's kind of the point, right? The heat is being released globally.
Right.
And like that may be, and so like Dan from Creation Myths, thank you. He's referring to the Soviet H bomb. But like 57 megatons is like less than 1% of the energy of the like order of magnitude what we're talking about that is the heat problem.
Many orders of magnitude below for sure.
Okay. So that's like that might be
like if the number quoting off the top of my head was something times 10 to the 30th joules.
Yeah, so it's this isn't a good comparison. That may be the largest yield bomb we've ever made, but it's nothing compared. It's nothing compared to the energy scales that we're talking about with the heat problem.
Which the scaling issue is commonly a problem for creationists. They'll talk when we bring up the heat problem. The number is for the whole Earth, mantle and crust, is 1.6 times 10 to the 30th. It's the amount of heat just from radiation.
Okay.
It's not the whole like moving plate thing. And so they'll often look at things like, well, what about like coal formation, or what about like the limestone or something? And that thing, it'll be like 6, 7, 8, 10 orders of magnitude lower than the amount of heat you need to get rid of. You know,
gotcha.
Like, so small you may as well not even mention it. I don't know what this guy's going to talk about.
Yeah. Like creationists, I've noticed something that like they tend to think large numbers are impressive, right? That they like to memorize large numbers. But then also don't have a good understanding of like order of magnitude thinking.
I mean, times 10 to the 26th and times 10 to the 30th, it's like only 4 away. Like it's right there, you know? They're basically the same.
No. Oh, that hurts. That hurts. Okay. Also, I'm going to say hi to Scott Duke and Icarus and Silver over in the chat. Hi, team. I'm glad you guys are here. Okay. All right. Let's keep going.
It's not only the amount of energy that is involved that matters, but also the heat transport. In other words, where is the heat? So heat transport then. How do we get heat from here to there? Basically, there are only 3 ways to do that. Heat flow, conduction, and thermal radiation.
Whoa. Does he mean convection when he says heat flow?
No, I think I've heard him talk about this before, and if I remember correctly, he tends to confuse conduction and convection like they're the same thing.
Mm-hmm.
But there are 3. It's just convection, conduction, and radiation.
Yeah.
You got the right number.
Yeah, he got the right number. So I'm interested to see what heat flow. I was about to be like, we went like 30 whole seconds without pausing because I was like, this isn't wrong.
Well, I mean, I guess you could, if you wanted to talk about like mass transfer. So like if you had hot mass in the system and you move the hot mass out, it's not exactly heat transfer, but you are evacuating heat from the system.
Yeah.
So like if the creationists, if like, I don't know, had all the radioactive rocks and then they were ejected into space, well, then it wouldn't be a problem anymore because they're like far away. You move them the hot matter out of the situation.
Yeah, I guess that's
not exactly heat transfer, but it would accomplish the goal.
Yeah, that would be a way you could like. Yeah, so normally we're talking about heat transfer. We're talking about like processes that like humans don't do, right? So like, yeah, absolutely. If I take a hot rock, right? Let's say I heat a rock up by my campfire, and then I drop that rock into my water, a pot of water. That's going to heat up the water. But I could also reach in and pull that rock out and remove that heat source. Right. But like natural processes are just conduction, which is a hot thing touches something that's not hot, and the not hot thing steals some energy from it. Sorry, this is me explaining for the folks at home. I know what you think. I know you know what these things are.
Yeah.
Convection is like a lava lamp or water boiling. That's you're physically moving material in a convective plume, and moving fluid. Sorry, I do atmospheric science stuff, so that like convecting plumes we talk about those a lot.
Sense. I'm a mechanical engineer, if anyone doesn't know. So mechanical and nuclear.
Okay. And then radiation is EM, electromagnetic radiation, electromagnetic waves, transferring energy. That's an important thing because it's the only way to transfer energy across a vacuum is radiation. Anyway, all right, let's hear him explain it.
If none of these is available, the heat stays where it is. Flow
well,
is
radiation's
like
always available.
Radiation's always available.
Like it doesn't, you can't stop black body radiation. It's just gonna happen.
It's just gonna happen. You can't make something not cool, right? You can't do that.
Yeah.
Okay.
That is hot, and the material moves. So this is flow, and this is no flow. Conduction. Conduction is heat transport by material that is.
I would call that what he just referred to. I would call that convection. Because it's like a fluid is moving.
Yeah, a moving fluid you're going to have convection.
Yeah, okay.
Touching each other. So consider we have a hot material touching a cold material in a closed environment, and the material doesn't move. After a while, all this material will have a medium temperature. So this is a good conductor, and this is a bad conductor. Radiation. Radiation is heat transport by emitting light. If it's very hot, it can be red, yellow, or even white. But usually we don't see it because the majority is infrared light. So this is a good radiator and this is a bad radiator.
No.
So
technically,
the radiation doesn't depend on the materials. Well, I guess the emissivity constant would change, right? Mm-hmm. But like it's mainly the temperature. is what.
Right. Well, and like, yeah, so it's the for radiation, for radiative heat transfer, that's a function of not the thing that's hot so much as it is the like what's around it, right? So it's harder for that heat, that EM radiation to move through, say, water than it is air.
Well, it's also a like you're getting rid of radiation based on your temperature.
Right.
Stefan-Boltzmann law. But you're also going to be receiving radiation based on the surrounding medium because it's also radiating heat. And so that's like if you had two bodies that were if you had like a ball that was the same temperature as the water around it, they're both emitting radiation. It just equals out because it's the same temperature.
Right. I just like, I don't, this is of his examples. I don't like this one because
this one's a little misleading.
Presumably if like, let's say you just took your tea kettle off of that burner, right? Then those two things are the same temperature. Like they're equally good at emitting radiation.
Sure. Yeah.
Yeah.
I mean, if it's primarily temperature, it's gonna.
Right. And this is like they're both in the same room receiving the same outside stuff. Yeah. All those details. Okay.
All right. Well, is it like a B+ so far at least?
Yeah. I give him a B+.
It's possible to trap heat like heat inside the Earth. Let's take a random example. Assume we have a large piece of rock and suddenly parts of this rock gets molten for some reason. It expands a little and now let's add water to it. And let's assume the rock contains enough heat to boil all this water away. So the water then starts to boil at some point and the lava is starting to cool down. The lava sinks slowly, causing some places where hot rock goes upward. And after a while, a solid layer forms on top of this molten rock, and then eventually we would have a situation where a solid layer isolates the hot molten rock from the water. So we'd end up with trapped heat and still a lot of water on top. So for all the oceans to evaporate, all heat must end up in the ocean, which does not happen.
So you can't trap heat indefinitely. You can slow it down. So like that solid blanket is going to slow down your heat transfer between the water and your magma. But the heat's still going to leave. It's just a matter of like the rate, right? So you can't trap it indefinitely. But I guess if you're only worried about a year, Noah's flood is all they care about, then I mean, I guess over that time scale, maybe you could trap, I don't know.
Well, but like, okay, so like right now there are pockets of molten rock, right? Like below us. Yeah, Dan, absolutely. Conduction is still going to happen.
Sure.
And then it also matters how hot that, like, because we're not talking about just enough energy to melt a little bit of rock. We're talking about enough energy for, again, I said melt planet Earth several times over. I'm sure it's more than enough to vaporize a good portion of it.
The number from my calculations, like I said, so the thing with the heat problem is the heat isn't coming from the mantle, at least not most of it, which it seems to be what he's going at. But the actual heat problem comes from the radioactive materials being in the crust already, because the crust is enriched. The crust is like a third of our uranium and thorium, and so it gets about a third of the heat. And so the crust is only 0.4% of the Earth's mass, but it's getting a third of the heat. That is a disproportionate amount. And so all of that heat being pumped into the crust is going to vaporize the crust. It may not destroy the Earth. Like, I mean, sure, there's going to be some spherical shaped rock thing still there afterwards, but that's not going to help Noah and everybody else when the crust he was standing on turns into gaseous vapor and blows him into space, like.
Right. No, absolutely. So, so an important thing there is that like crust there includes that like ocean crust that's below the oceans. So that enriched part of the crust there, that's just from the accelerated decay that you need, right? That they claim occurred all during Noah's flood. So yeah, we just put every single ocean on top of like the burner on your stove dialed up to nuclear.
It'd be like if you had your burner on your stove as high as it would go, and then you took like a thimble of water and threw it on the stove. Like that's, it's just going to immediately evaporate.
Right. So this process that he just described, I mean, it's not untrue, but it's also unrelated to the problem that we're talking about. So that's a real process that occurs, right? When you're like, that's how you make new continental crust. You got to melt some stuff. It's got to hang out down in like upper mantle, lower crust for a while, make some granite, some feldspar, if you will. And then eventually like pop up,
Yeah.
you know,
it's true, but it's not really relevant. Like changing that from a liquid to a solid, it's getting cool. Heat transfer is driven by a delta temperature. So if the temperature at the interfaces, there's less difference, you're going to have less heat transfer. So your gradient lower down is going to go up. Like it is going to slow down the heat transfer, but it's not going to eliminate it.
Right. And certainly this process that he just described is not the process that we're talking about of like the sudden release of radioactive.
Yeah.
Like,
and it's also not going to happen because that crust is going to continue to be having heat dumped into it by the radioactive material in it. So it's never going to get to the point of solidifying because it's
Right. So when this process happens naturally today, usually what happens is like a subducting plate brings some water with it down into the mantle that causes some chemical reactions, which cause melting. And now we get this like liquid pocket that's, you know, geologic time later going to do something interesting. So like that's that process, which is unrelated to the thing we're talking about.
Yeah.
You see, it's possible to touch freshly solidified lava with your shoes shortly without them catching fire. For your own safety, I highly recommend not to do this, but it is possible. So let's take a look at what will happen if continents shift quickly, exposing hot mantle material.
That's not how geology works. I am not a geologist, but like continents moving doesn't directly expose the mantle.
Right, because the crust is like over the whole Earth, right?
Mm-hmm.
Like, again, I'm also not a geologist, but I don't feel like there's like veins of like gaps with like rivers of magma. I don't think that's how that.
No.
Yeah.
So one, if we could dig down to the mantle and look at it, it would be a solid, right?
Mm.
That's a common misconception because most people know that like the mantle convects, and it does. It's a solid that convects over geologic timescales, which is very cool. But if we were to dig down and look at it, it's solid rock, right? It's also true that like, is the mantle warmer than the crust? Yes, it's not a sudden change, you know?
It's a gradient.
It's a gradient. It's a nice temperature gradient. So the temperature at the top of the mantle and the bottom of the crust is the same. And it's not hot lava, right? Lava is what happens when volcanoes erupt, right? When we're getting other types of processes. Again, the mantle isn't just liquid lava floating around. So I'm not quite sure what he thinks geophysically is going on here, but it's not this ain't it. This isn't what's going on. Okay.
Say the left is South America, the middle part is lava, but this is what is going to be the Atlantic Ocean, and the right is Africa. The lava is lighter than the solid rock, so it expands. Not only does this boil the ocean away there, but it also pushes the ocean away there because of the expansion. The result is that it would start to rain like crazy in colder areas, and that is on the continents. So
What? Sorry about the ad.
Oreos? Yeah.
Hershey's Cookies and Cream. Yummy, yummy.
This episode brought to you by...
I'm not sponsored by Kohl's. Kohl's, sponsor me. I'll wear that hat all day long.
We would have a situation...
All right. Okay, what did he just say? Because I'm very confused.
He said, I guess because it's going to be hot right here and cold there, that would lead to rain. Is that... You're the weather person, so...
All right. Let's think about it. All right. No. So sorry, because he has water evaporating and just the moving, like east and west, right? Do you see that? Like,
Yeah.
so,
I see like the plumes coming out of his
so
lava pit.
so that's not real life. So like one sure, if you have a suddenly like the ocean gets very warm, but like again, this would only be it got like warmer, not we dumped so much energy we could melt the earth into the ocean, right? This is like normal processes. If it's
at this point, I feel like we're beyond rainfall. Like rainfall is the
Oh,
least
yeah.
of our concerns. You know?
We're way beyond rainfall, but also if it was going to rain, it wouldn't look like that, right? So you would just have you would have evaporation, right? And that tends to go straight up, right? So that's going to go mostly straight up, and so you would get clouds and rain back on top of where you were evaporating from.
Right.
If those large, let's say we're making a large storm system,
like a hurricane, for example.
Absolutely not. No, well, what? Sorry, to make a hurricane, you can't just heat up the ocean and make a hurricane. You have to have a pre-existing low. You have to have really weak wind shear. You need a lot of different ingredients already in place before that heat of the ocean matters. So we have a bunch of evaporation. We make clouds. We keep evaporating into it, so we're going to get precipitation. Those guys, like those storm clouds, would just follow. Like they're not going to split east and west, right? Because that's not how global atmospheric circulation works. Like you probably see them move poleward, so to the north in the northern hemisphere, to the south in the southern hemisphere, and then a little bit following the upper air currents. So probably moving a little like maybe getting caught in some of the like global westerlies. So head towards the east, right? So like that's what we would expect, not that nonsense. And there's also like, if you had a strong temperature differential between, well, that's so like, I think he's trying to get at hydrostatic balance, or maybe he's not, and I'm giving him too much credit. Because hydrostatic balance, right? That's how you can get like air circulation between like warm oceans and cold land, because you're going to get a pressure differential because you get the temperature change, blah, blah, blah. But moral of the story, this process wouldn't happen as drawn under any circumstances. And you wouldn't just get evaporation for the levels of energy we're talking about.
I don't know what he is getting at, but what I can say is I actually did the math for the ocean to like if it just how much it could absorb, the whole thing.
Okay.
Because that's something that they often try to credit.
Yeah.
So the ocean, I did one with his wrong number for the ocean. I'll get in a second, but it's not enough. If you boil the whole ocean, you're still orders of magnitude below where you need to be.
Right. Yeah. Okay.
Where the ocean is flooding the continents, and the lava has a lot of freedom to expose its heat to the sky and the universe. At the edge of the continents, the water touches the hot lava, enhancing the solid.
Oh, okay. Light blue are supposed to be continents. Dark blue is ocean. And then orange there is a river of lava.
From the exploded like crust that like, erupted. Okay.
I think that's actually supposed to be the Mid-Atlantic Ridge, but that's not how the Mid-Atlantic Ridge formed. You can't get the Mid-Atlantic Ridge quickly, is the point. Anyway.
So that water plus everything else George Bond added in, which was other stuff, but the water was the biggest part, was 5.2 times 10 to the 26 joules. So 4 orders of magnitude less. That's water plus everything else.
Right.
So not even like a fraction of a percent.
Right. We're off by 1,000, a factor of 1,000.
Yeah.
We're off by, I can math. We're off by a factor of 10,000.
4 orders of magnitude.
Yeah.
10, 100,000, 10,000. Yep. Math is hard.
Math gosh, I shouldn't have said I have a degree in it. Then I become incapable of doing basic calculations.
Well, see, when you have the degree, you don't work in numbers anymore. It's all just letters and stuff, right?
Right.
Yeah.
So actually, at my undergrad, we had a joke that if you were like going out to dinner with a group of friends, the person to split the bill had to be the youngest non-math major because they were the most likely to be sober and able to do math.
I definitely have calculitis. Like
Yeah.
I can do calculus, but if you want me to do arithmetic, I'm going to need a calculator.
Yeah. I got over that, by the way, because I started tutoring like early high school kids, which was very helpful. My algebra skills had gotten rusty and I'd forgotten.
Yeah. I've had to brush up with my kids being in high school. One of them was like talking about the equation. This is completely off topic. One of them was talking about the equation of a line, and he wanted me to do the slope, and it took me a second to like put that back in my brain, you know. And I paused for a second. He's like, "You're an engineer. Like, why don't you know this?" It's like, well, I know the slope is 2 because I just take the derivative. I'm trying to remember how the stupid way you have to do it, you know?
Right. Wow. Okay. Enough fun math talk.
All right.
All right.
Back to the
solidification process there. Because it solidifies, it shrinks and becomes denser than the continents, so it leaves more room for the water there. The molten lava is being squeezed out horizontally and wants to flow on top of the solidified lava. But there's water there, so it also starts to solidify. So the water is slowly pushing the molten lava towards the middle, and eventually 2 layers of solidified lava lean on each other, and this causes a closing seam, a closing midpoint, which we identify today as a mid-oceanic ridge.
The process that he just described, like, doesn't happen quickly. That's not what that would look like if it wasn't occurring over millions of years.
Right. This is what, if you fast forwarded it, like if you took a video over 1 billion years and fast forwarded, it would look like that. But the process they're talking about is not this process.
Exactly.
When it comes to thermal radiation, we can actually calculate how long this would take. For that, we need to use the Stefan-Boltzmann law. And the result of this formula is energy per time. You get it by multiplying some constant value with the emissivity, the area, and the temperature. But the temperature is in the 4th power in this formula, resulting in a tremendous nonlinear process. So the answer is in watts or joules per second, and Stefan's constant is a very small number. The emissivity is a property of the material. We're going to calculate.
Okay, all of Earth's crust isn't basalt, but okay.
It won't matter.
This for basalt, which is what the oceanic floor is made of. The area is in square meters and the temperature is in kelvins. Let's give an example first. If we would have 1 cubic meter of basalt being exposed for only 1 square meter, how long would it take to solidify? And like I said, it strongly depends on the temperature. If it would cool down from 2000 Kelvin to 1900 Kelvin, it would take 399 seconds, which is about 7 minutes.
Okay, so hold on, I'm trying to think of what they're doing.
So what he's doing is he's using the black body radiation to get a energy per time.
Right.
And then I assume he's going back to like specific heat or something to get like the temperature.
Because he would have to. So what he's doing is taking a change in temperature, and because the black body radiation, that's just like energy is or.
So what I think what the black body radiation, what you get out of that is energy per area, so watts per square meter, and this is 1 square meter, so that just goes away. And then I think what he's done, he didn't say this, but I bet what he's done is he said, okay, for this, using this specific heat of basalt to go from 2000 Kelvin to 1900 Kelvin, it would take this much energy, and this is the wattage. How much time would that take? I bet that's what he did.
Okay, that makes sense. I'm just like, because I'm very familiar with the Stefan-Boltzmann law, but I don't know how to use it to get to time, right? If that makes sense.
Yeah. Well, it gives you wattage, which is joules per time. Right. And then,
right.
And you could use that to calculate.
Okay.
You'd have to assume like
you need to know that energy. That's the part that was driving me nuts. Okay.
Yeah.
Cool. Okay.
From 1000 to 900 Kelvin, it takes about 2 hours. From 300 to 200 kelvins, it takes about 20 days. And from 100 to 0 takes forever. It will never reach 0.
Right, nothing will ever reach.
So this is very
0
strongly
Kelvin.
nonlinear.
That's fine.
Now assume we have 2 blocks of rock. They are made of the same material, they are equally thick, and they are only exposed at the top. But one of these blocks is a lot larger than the other. Which would cool down faster? If we use both the formula for heat capacity and the Stefan-Boltzmann law, we see that the area plays a role in both.
Yeah.
More area means more heat capacity in a linear way, but more area means more thermal radiation also in a linear way. This means that in the end, for the cooling down time, area isn't relevant. It's the thickness that matters.
Kind of. In the contrived situation he's talking about, where like you've got a unit area, it's not that's the only exposed area, it's the same temperature, there's nothing else different, and it's all emitting at the same rate per unit area. In that case, yeah, sure, it doesn't matter because per unit area it's all the same. Right. In reality, you increase the surface area, you're going to increase heat transfer. That's how heat transfer works. But
exactly.
So we can make the formulas a little bit simpler. And now we can calculate the thermal radiation for a scenario.
Okay.
So what he skipped there is he's talking about the heat capacity. So he didn't show this, but he used the I bet he used the specific heat, like I said, and the volume of the rock to get the mass. And so that I think that's the stuff he's got behind the scenes, and that's why he's bringing thickness in.
Right. Okay. And so then,
because the thickness would tell you like how much heat you have. I guess it'd be like your well.
Right.
Yeah.
Right. And so here's our equation, which it looks like the Stefan-Boltzmann law. So energy emission over time. So that's watts is Stefan-Boltzmann constant times emissivity times temperature to the fourth. Okay, yes. Sorry, this is Stefan-Boltzmann constant.
Yeah.
This is for a gray body, not a black body. That's
black body has an emissivity constant of 1.
Exactly. Okay. All right. So let's
can calculate the thermal radiation for a scenario. What if the entire oceanic crust was molten at the same time?
Okay.
How long would it take to solidify? We use these variables. The thickness of the oceanic crust is about 7 kilometers on average, and we use temperatures that are normal for molten lava.
Okay.
So the problem, what he's missing here, is that it's not that you have the crust is molten and then it's done and then you need to cool it down. That's not what's happening. What's happening is you have heat generation constantly through an entire year. You don't. I mean, it'd be even worse if it was all at one point. I mean, then the crust would violently be ejected into space, sure. But the point is like you're not. It's not. You have an input as well, not just an output. And so you've got the movement of the crust. You've got the radioactive material dumping heat, and you need to eject that heat, right? And so it is true that it is a strongly nonlinear process because it's temperature to the fourth. That is true. Unfortunately, the amount of heat that they need is just so mind-bogglingly huge that doesn't matter. I have the math for how much it would be, because I've done this problem before. I can wait till his answer if you want.
Yeah. No. Tell us what the right answer is, and then let's see what we got.
So the average. So I'm a nuclear guy, so I just look at the radiation.
Yeah.
And the amount of heat produced, the average heat produced by radiation in the crust. So every day. So if you took that, I take 2 billion years worth of heat and compress it into the flood year.
Mm-hmm.
And then so if you just divided that by 365, which isn't exactly right because it's a slope, not linear, but it's close. Mm-hmm. So the average heat per day is 1.59 times 10 to the 10 terawatts. So it's doing that much like all the time.
Mm-hmm.
Just for scale, humans produce about 17.7 terawatts. So that gives it's 10 or 8 orders of magnitude bigger than that. So a lot of heat. So you know how much energy you need to reject per second. You can just throw that in the Stefan-Boltzmann law and see what temperature you need. In order to reject that much heat, like consistently, you would need a temperature of 4,569 degrees Celsius, which lead melts at 330.
Yeah.
And that's the temperature in the space, like at the interface between the atmosphere, like that's where the rejection is happening, right? So the temperature down where Noah is even worse. Yeah, that's so. And it's not like your heat magically teleports from this magma where the heat's being generated, the crust, to space. It has to go through everything on the way, heating it all up as it goes. So it's not like, oh, we can reject it to space and just don't worry about this part. No, it's going to go through the ocean and the ark and all the little baby animals and Noah and then to space, you know?
Yeah, no, absolutely. I also love that his end temperature here is 1,000. Let's just use his numbers. Let's look at that end temperature of 1,000 degrees Celsius. Like, I'm sorry. Do you think Noah and the baby animals are going to be alive? If it's 1,000 degrees Celsius, so ignoring like your more accurate numbers, right? His model doesn't allow things to live.
Yeah, you've cooled it all the way down to lethal levels. Like what it?
Yeah, like the
We're
average...
still in ocean boiling levels.
Yes,
yeah,
yes, right. That's, gosh, yeah.
And let's also just, as an aside, you can't just melt the crust and not leave any sign of that. There's all kinds of signs, like you leave evidence when you do things like that, or often more accurately, you destroy evidence.
Yeah. I think a great way, like if you leave your chocolate bar in your car and then pick it up, it's a liquid inside, and you run it into your freezer, it looks different. You can tell it melted once it re-solidified, is my simplified explanation for that.
Yeah, very good.
Yeah.
Which is a starting temperature of 1,600 degrees Celsius and a solidification temperature of 1,000 degrees Celsius. For this calculation, it is better to integrate the Stefan-Boltzmann law to get accurate results. Since the temperature is so high, the energy emission is huge. Remember, the temperature is in the fourth power. It takes 1 year and 150 days to solidify. So not billions of years, not millions of years, not even thousands of years, only 1.5 years. Because
Bro,
the solidifying...
Noah's still dead.
Noah's still dead. Yeah, absolutely. Noah's still dead. And like, I mean, like, okay, my guy, like, you know, a great thing to remember is like, so why is Venus a runaway greenhouse? Why does Venus have a runaway greenhouse problem, right? How is the temperature, the like equilibrium temperature of Venus's surface is hot enough to melt lead, right? It's insane. And their crust, Venus's crust, like it solidifies for a second and then it just remelts, right? So this is actually this is a fun fact. Venus and Earth have effectively the same amount of carbon, right? All of Venus's is in its atmosphere. Ours is in people and rocks, right? So if you had a process like this, where think about it, if we vaporize all this stuff, right? If we didn't have liquid water, right? If we vaporize that, that would also put all of that carbon into the atmosphere, and then we would have a runaway greenhouse problem.
Good point. Yeah.
So there's also that.
That would also slow down the heat transfer,
right?
And then bake Noah even longer.
Exactly. So Venus is the way it is because it's too hot to have liquid water, right? And so that liquid water can't interact with the carbon to get the chemical reactions to get Earth-like processes. Anyway, so there's that. Fun times. Anyway, and
I'm wondering how many times Noah's going to die by the end of this video.
He's died a lot. One, like, think of how crazy the tsunami, right? The tsunami that came from the Fukushima earthquake, right? Was, and I'm sure you know this, you're a nuclear guy. But that tsunami was, so when they built the nuclear plant, right, they build it to have a tolerance to be able to withstand not only like the strongest natural disaster that's ever happened at that place, but then also like scale that up a few times. It's like, okay, this is we're built it to withstand stronger than anything that's ever going to hit this place, right? And then the Fukushima tsunami was way stronger than what they had ever anticipated, right? So false. That is one earthquake, right? That's one earthquake.
One like normal level earthquake.
Right. It was pretty intense. Like
intense, but like we're not talking like biblical end of the Armageddon.
Exactly. We're not talking about biblical end of the world. So that's one, and that destroyed modern infrastructure, right? Now imagine what would happen to a boat made of wood on the ocean having Fukushima plus level earthquakes happening left,
building
right, and center.
sized, like skyscraper sized waves, you know.
Right. So that's another. So one, if your Mid-Atlantic Ridge is forming that quickly, like that's also going to kill NOAA. Yeah. Okay. Latent heat fusion?
I think he means latent heat of fusion.
Okay.
Yeah. Not like fusion like a star, like fusing from solidifying.
Okay. Sorry. That was...
You never know.
Never know. Let's see what he says.
The process itself also releases energy. This is called latent heat fusion. But also this takes only 2.3 years. So if we would melt the entire oceanic crust at once, it takes only 3.7 years to solidify using thermal radiation alone. Water enhances this solidification process, so we are actually very much in the right order of magnitude.
I mean, only if you still have liquid water when that latent... So like, okay, what he's saying is for latent heat, right? So yes, absolutely. When things change phase, you can either absorb or release latent heat. If we're going to go from
the temperature stays the same. So when you do a phase change during the transition period, the temperature is constant. So if you have ice water, it's 0 degrees Celsius the whole time, no matter, as long as it's well mixed, however much ice is in there, and then you have the change. So and that's as contrasted to sensible heat. So if you've got the heat coming in, it's fusing, then you hit a plateau of temperature, and it's going to continue to solidify, and then you get to your saturation point where it's completely solid at that point. Mm-hmm. So that, I guess he's saying that would take 3.7 years. And it is true that having water, so that's just with radiation. If you have then conduction and convection, probably, because the water's going to be moving and you're also touching, so you're going to have both of those modes. Then it would be cooling down faster than just radiation. However, that's just forgetting the fact that you're having heat dumped in all the time. Like the order of magnitude, we're talking like the water's gone, bro. Like that left day one, you know?
Yeah, that's got. So yeah, if you dumped in that much energy and then one self-contained the system, right? No matter was allowed to escape to space, and didn't touch anything else and let it come back. Maybe.
Even if you dumped all the energy all at once, you'd have just as much. Like the water would still boil, would still go away. Like you still have all the same problems. If you dumped if the heat problem was much smaller than it actually is, then maybe this would work.
Maybe. Yeah, but
if we were talking about a completely different problem, then maybe.
Excellent. And I'm so glad you explained latent heat. I don't know why I talk about it all the time because I have to, because of like latent heating of latent heat of evaporation for like cloud formation, all that jazz. I always get it backwards every single time, especially when I'm on camera, right? Or lecturing. I never say it right the first time. So I've given up. I always draw it on the chalkboard and I just like read it because
just draw the diagram.
Just draw the diagram directly from my notes. Never speak off the cuff. So
an easy way to remember it is that sensible heat increases and decreases temperature because that's what you'd expect heat to do because it's sensible. And latent heat is the not sensible one.
Right. I like it. Okay. So yeah, this is nonsense.
Yeah. Is
what this is. And yeah, you need liquid water for it to help. Anyway. Okay.
Magnitude for the Genesis flood. If you see my other presentation about the solar system, you see that the evolutionary timescale for things like the moon are very far off.
Why?
When a crust is solidified, it's still
gonna
quite
throw that
hot,
out there, don't worry.
about 1,000
Just gonna make that claim.
The moon is also a problem. Anyway, moving on.
Anyway, anyway, no evidence. Let's go.
degrees Celsius. Then conduction takes over for the cooling down process. We can also calculate this. We have a formula that says that heat conduction per time is the thermal conductivity time.
That
Thermal, okay.
looks mostly correct. I mean,
Yeah.
This was. I'd have to look at my notes to make sure it's 100%. But you got your delta T there. You got your surface area, which I don't know why he's dividing by thickness, but whatever. Maybe that's like how much. Maybe he's trying to get to how much heat there is. It would be the surface area that matters. Right. And then the thermal conductivity, which is how good the material is at conducting heat. Plastic has a low conductivity, metal has a high one. Yeah, okay.
Okay.
Close enough, probably.
Yeah.
Times the area.
Subway has
Sorry.
so much new.
Not now, Subway.
No time for
We have the big sponsors.
So many. Listen, should I get an ad blocker? Probably. But I won't make you listen to
times
it.
The temperature difference on both sides of the material divided by the thickness of the layer. To do this properly, we must divide the materials up in smaller layers.
We're going to do it in Excel.
Wow. He's doing finite element analysis in Excel, man.
Wow.
That is kudos to him.
Yeah, I'm actually a little impressed. That takes some patience.
So what he's doing, if anyone isn't aware, so heat transfer is going to change over time, right? Because you've got your heat here and your cool here, and it's going to heat up along the way. But as these things are changing in temperature, that in turn changes the rate, because it's that delta T that matters, right? And so as you're moving towards thermal equilibrium, the rate of heat transfer is changing constantly. So you can integrate it, but it's actually a really hard problem to integrate. You'd have to probably do it numerically. So he's doing it like brute force via Excel. That's, man, applause. That's intense.
Ooh, I once had to, for an undergraduate class, I had to write an Excel program to do fast Fourier transform. That was evil. And then after that, I was like, screw it. I know we don't. I just did everything. I did MATLAB. I like learned MATLAB after that.
There are programs specifically for this.
Right. Anyway. Also, hi, David. Thanks for popping in. Yeah. Okay. Okay.
Madman. I wouldn't use Excel.
Because each of these layers have their own temperature, and thus they have their own amount of heat energy and their own conduction speed. All these layers give their energy to their neighbors, and only the top layers releases that energy to cool the whole lot down. So we start with a lot of layers that are 1000 degrees Celsius each, except for the top layer, which is a room temperature. Remember, there's water on top.
Wait, why is the top layer room temperature?
I don't know. You wouldn't have a disconformity like that in your temperature.
No,
so,
you wouldn't have that.
So it's going to look, I'm trying to see how to do it. So it's not going to be like, you're going to have a sharp decline.
Right.
But the temperature of every constituent piece matches the temperature of the next piece.
Right.
Well, I mean, unless you're like in the weird magical hypothetical where things were room temperature and then boom, they're not. Like in that, if you just magically swapped out the crust with like a super hot crust, but that's not physical. Yeah.
Right. And there's a few people in the chat going, why room temperature? And that's a great question. I don't know why it would be that. That doesn't make sense to me, because
why not? I don't know.
I guess why not? Because really, to do this, what you'd have to do is the like thermal conductivity of the crust, right? And get that to the like, okay, how much heat is being released at the Earth's surface. Mm-hmm. And then switch gears. And if you wanted to, for order of magnitude, just like a back of the napkin thing, I guess you could do like, let's consider like the atmosphere as like a slab, like a one solid slab, right. Or even what if it was touching space? You
could just model it as infinite heat sink that never changes temperature.
Yeah,
which is not reality, but you could like do that if you wanted to get a quick number.
Yeah. But you would need to then like, okay, now we have to deal with the atmosphere to get it accurate. Right. But yeah, because I mean, room temperature. Because I mean, I guess I don't. Yeah, sorry, that disconformity is blowing my mind. I'm like, I don't know how you got that. I don't know why you did it that way.
Yeah, it certainly wouldn't stay that way for long, even if you did it by magic.
Right. So
yeah,
I don't.
You don't get this jagged like disconformity in your temperature.
Right. So if we were doing, just so team like listening, so if you were gonna do like, okay, Earth is hot and it's radiating out to space, right? In reality, if you want to know what is the temperature of space, right? Well, it actually matters where you are, because if you're close to the sun, it's hotter. If you're close to the Earth's atmosphere, there's not a hard line that signifies the end of the Earth's atmosphere and the start of space. It's just a gradient. So temperature is just going to drop off. Sorry, he's breaking my brain. I'm just going to let him keep talking. It's
not going to matter because because again, this isn't an instantaneous problem. The heat.
Exactly.
I've already said it.
Yeah, I'm trying to fix his math, and I realize that's the wrong.
It's hopeless.
That's the wrong way to be approaching this, but I'm struggling through it. Okay.
Top, which consumes a lot of heat. The layers are 50 meters thick each, and we're using a time interval of about 100 days to calculate the conductivity step by step. And we represent the temperature with colors. Red is 1000 degrees Celsius, yellow is 500, and green is 20. Here we display a layer of 7 kilometers thick. This is what it looks like after 90 years, 1000 years, 2000 years, 3000 years, 4000 years, and let's stop at 4500 years. If we are looking at the Genesis flood, it could be that this is close to the time that has passed since. There are uncertainties at when the flood year was, which is a subject for another discussion, but let's just see what the result.
So he's trying to say that because this kind of sort of matches what we see today, then it's fine. Like, observation confirmed, I guess. I think what he's okay. So if we ignored like everything that happened during the flood year, all the heat that's being dumped in, all the heat that's going through NOAA, etc., and I think what he's really talking about functionally is you say, okay, the flood is over. Now what?
Okay.
Now what happens? And then you might have a situation like this, because then accelerated nuclear decay has stopped, the plates have stopped, you're not having heat dumped in anymore. Like, then maybe some analysis like this could be useful. He's still ignoring the fact that you've got like still heat being come into the system and stuff like that, because radioactive decay is still happening, but not on the same level.
Right.
But again, like that's what he's done is he's addressed the heat problem by ignoring the heat problem completely and talking about some other thing.
Yeah, absolutely. And the other thing is that like those temperatures that he was showing, even in this model, like I don't want to live on Earth's surface when it's like that. You know,
no, like NOAA got off the boat and it was still 1000 degrees Celsius on the crust. Like, what? Talk about hot sands, you know?
Yeah, like no, thank you. That looks gross, and I don't like it. Yeah. Okay.
This after 4500 years. In this scenario, all would have cooled down, and we would find the maximum of 590 degrees Celsius at 4700 meters depth.
Remember, we still have a lot of volcanic areas, which are in the basaltic oceanic crust.
Is that, I don't know, is that the temperature you actually find at 4700 meters?
I have no idea. I have no idea. I suspect not, but
because it wouldn't surprise me if the reason he has that room temperature air is because that's the number he needed to get to the number he knew he wanted. You know,
that's fair. Yeah, I wouldn't be surprised. I would be team. There's like he broke a rule of like doing your physics homework, which is like state all of your assumptions up front, and justify all of your assumptions. So like that 20 degrees is blowing my mind. And then I like this is like so. There do volcanic pockets exist now? Yeah, and those are warmer than the place around it. Oh shoot, I've lost my mind. No, it can't possibly be that hot at 4,700 meters depth because it's a solid. Still a solid. Anyway, just solid silica material, solid rock. Okay.
So conductivity is happening there. Since these are still hot today and only a few kilometers depth, it means these volcanic areas could not be millions of years old.
Oh, shoot.
No,
I read
man.
4,700 kilometers, and I was thinking like we're deep in the mantle and into like into the core. That's 4.7 meters. We're still in the 4.7 kilometers. That's still in the
Still in
crust.
the crust. Yeah.
It's still in the crust. That's not real.
Okay. And what he just said is like these pockets of lava show it's not millions of years old. Again, there's still heat being produced right now.
Right.
In like we can detect the neutrinos from the uranium and thorium decay today.
Yeah.
So it's definitely still happening.
Yeah, and there's other processes that like I talked about earlier about that happens on plate boundaries that melt small pockets, blah blah blah. And also turns out the mantle isn't a uniform temperature, right? You can get hot spots or thin places and all that jazz.
Or blobs, perhaps.
Or blobs. Yes, you can get warm blobs. Dude, I do Arctic research. We've talked about that warm blob a lot. Is it connected to the NAO cycle? That's the question. That only I am asking, I think. That's fine.
This calculation shows that it can only stay hot for thousands of years.
No!
Now, when it comes to heat, there's some pretty...
No, that's not how that works.
Bro, so if you're gonna analyze a problem with thermodynamics, right? This is a heat transfer thermodynamics problem. You've got your heat that you have or whatever, but there's also a term, heat out, and he's really focused on that. There's another term, it's heat in. That he's just chopping off the equation he doesn't like. You can't just ignore the heat that's coming into your system. That's like saying, oh well, this meat is never gonna cook because the temperature of the skillet right now is not hot enough. Well, you've got heat coming in, man. That's
yeah. God.
So dumb.
So dumb. Okay.
Weird phenomena that come into play. One is a thermocline. You may wonder how fish could survive such a scenario. Let's say we have regions with hot water and regions with cold water. Then there are also places where the hot water flows on top of the cold water. The hot water kills the fishes. Yes, we find a lot of dead fish in the geologic layers. And the fishes in the cold water can survive. The hot water is less dense than the cold water. This causes that hot and cold water don't mix very well. This causes a separation between hot and cold water layers, and this separation is called...
Okay, so no. One, this is being heated from the bottom up, right?
Exactly.
In this world.
Thank you.
Yeah, so this is what you're looking at is normal ocean. That thermocline does certainly exist, but that ocean is heated from the top down.
Right.
Right. So that's being heated by the sun.
So when you have a fluid and it's heated from the bottom, what you get is natural convection because you have your hot stuff at the bottom, it's being heated, and then it goes up, and then it loses its heat, and then it falls down, and then it goes up again, and then you get the circulation. So what you'd actually have is not this layer of hot, you'd have a better, well-mixed system. So all of the fishies would die. This situation would cause natural convection.
Yes.
Which I guess the chat just pointed out that he's not aware that convection is real because he didn't mention it in one of the heat transfer modes. So
Gotcha. Yeah, no, this is ignoring convection. This only works if you're heated from the top down. And also it's backwards in the Arctic Ocean, but that's fine. Okay.
The thermocline. Important for fishes, but you don't need that information for the rest of this presentation. Now the next issue is power law creep. Power law creep is a process that causes rock to become viscous without increase in temperature. How do you do that?
Hold on. I'm going to read his graph. That's sorry. Shear stress. Oh, okay. This is just stress versus temperature. So if you jack up the stress, you can make it behave plastic at lower temperatures. Cool.
Okay.
Well, let's assume we have several layers of rock. We put pressure on it, and we are going to push the top layer sideways. That is called shear stress. Then the middle layer will start to deform. In other words, it changes shape. Now if you put a gigantic shear stress on the top layer, the layer below dramatically changes shape. This process is very strongly non-linear and has to do with molecular structures breaking up and
So like he's not wrong here, but I don't know what his point is.
What does this have to do with the heat problem?
Right, I have no idea.
crystalline surfaces sliding on top of each other. It's very complex, but it has been tested in the laboratory. You can compare this with toothpaste. Toothpaste is solid until you put pressure on it, then it changes shape, but it will become solid again as soon as the pressure stops.
I'm not sure that's accurate, but who cares?
It's not really accurate. All right.
Who
Viscosity
cares?
of the rock up to 14 orders of magnitude, and thus it's very strongly non-linear. In very extreme conditions, solid rock can flow like water without increasing temperature. The last weird phenomenon.
I don't know that means the rock becomes like water.
No,
it's still like, I mean, even if it increases the plasticity or like it decreases its viscosity, it doesn't mean it became like water. But who cares? I guess nothing. What are we talking about?
Right. I have no idea what that has to do with anything we were talking about, because that doesn't have anything to do with the heat problem. Unless he's talking about, like, maybe he was trying to explain how you get different rock formations quickly.
Like maybe, but usually you'd have some kind of like bridging sentence or something.
Right. I need my topic sentence.
Yeah. Okay, thermoclines exist, but you're not going to need that anymore. Now here's something completely different, which you're also not going to need. Okay.
Right. Yeah, that's all. That's very silly. Okay, then let's find out what crossover depth is and see if that's related.
I'm going to show you is the crossover depth. We are used to magma rising up because molten material has a lower density than the same material.
No, that's not how magma magma exists in chambers, in closed chambers, right? And it's like you sort of keep melting stuff into it, right? And so you're just building pressure, and eventually it'll rupture. It's not, there's not magma floating through things.
Well, it's like water. We just learned that. So.
Oh, okay, cool.
Material in solid state. But it appears that molten rock is better compressible than solid rock. So if you put a lot...
Well, no joke, man. Any liquid is like slightly more compressible than the solid.
As a general rule, I'd agree. Yeah.
Yeah.
With pressure on lava, it will eventually become more dense than the solid rock. So magma that is very deep inside the earth sinks.
He thinks it's liquid when you get down to the mantle, right? And it's not.
He just said, like, if you increase the pressure a lot, if you're going to do that, then it might not be liquid anymore, even assuming it was to begin with, because the phase of matter depends on both pressure and temperature.
Yeah, and like the other thing that's kind of driving me nuts here, right, is I don't actually know what he's talking about, because he's using the wrong terms, right? And he clearly has a misconception of the internal structure of the Earth.
And I still have no idea what this has to do with the heat problem.
Right, yeah. So for anybody listening, guys, magma is liquid rock inside the Earth, but it's usually in the crust, right? But below the surface, right? 2, lava is liquid rock that's on top of the Earth's surface, right? So like if we could dig down to the mantle, we would not see magma. We would see solid rock. It would have a different chemical composition than the crust, but that's okay. Like to the untrained eye, I bet we couldn't tell the difference, you know? And so I literally don't know what he's talking about.
I have no idea.
Yeah, I don't know. Okay.
The point where the switches from rising to sinking is called the crossover depth. Depending on the rock type, the point where this happens is between 200 and 400 kilometers. This phenomenon has also been confirmed by multiple laboratory experiments. And very importantly, it shows that magma cannot come from deeper than 400 kilometers.
Okay, so material from the mantle that makes it to the surface that I'll take, right? That I don't know if that number is true, but I'll take that.
I'll take the whole thing. I have no idea why it's relevant at all.
I have no idea why it's relevant.
The crossover depth is about here. What I think that happened is that large impact plus the crossover depth plus power law creep is catastrophic plate tectonics.
And that's it.
And that's it?
I think A plus B plus C is D. Okay, bye. Like,
Okay, bye.
what?
First of all, what's the large impact? Are we like? I don't know. I don't know what it's talking about.
I don't know. Okay. I guess I understand why he mentioned, like, knowing that he was talking about catastrophic plate tectonics would have been useful beforehand, but
Right.
at the end of the day, like that doesn't matter. Like,
Okay.
this has none of that had anything to do with the heat problem.
Yeah. His math is bad, and even if you take his math at face value, you still can't get people to be alive.
Yeah. And none of this even talked about things like Noah has potassium in his body, which is also radioactive and enough to boil his blood. You know, like, so your Stefan-Boltzmann law isn't helping you there, man. Like,
no, it's not. It's not. So, so we have like assumptions he's making that don't make sense. We have some misunderstanding, or either he misunderstands or he just can't explain it. Of like interior structures of the Earth.
And he didn't. He showed some of his work, to be fair. But like, if we weren't coming to this already with an understanding of like how you do these kind of problems, there's no way we could check his work because he doesn't show half of it.
Right. Exactly. So that's really frustrating. And then like, yes, I think you and I, but even we're sitting here trying to like fix his model, or at least I was, and you were telling me like, no, sweetie, like don't, that's a lot. You're just going to get mad. But like I can't fix his model.
No,
you know,
that model was hopelessly flawed, is putting it charitably.
Yeah. Like we would need to start a new, we would just need to start from scratch. Like,
like his entire model is taking the problem like after the heat problem is over. Like after the flood year is over, then what happens? I guess I don't know. But that's like that's not the heat problem. So clearly, I guess he just doesn't understand what the heat problem is.
Yeah. So like, Team SFT, if you guys are watching, the heat problem is that to get the amount of radioactive decay you need, if that's happening over the course of that year, it's a constant input over the course of that year. So you're continuously heating. And how does Noah survive? And if it's because he built plasma shields onto Noah's Ark, then why were those instructions not written down? Because that would be very useful.
Maybe there's some oral instructions too, you know. Hey,
you
know, 30 qubits by 50 qubits. Also, here's some unobtainium shields. Those are going to keep
Wakanda has it. That's what happened.
It's also, Wakanda. I didn't mention it's plated in vibranium. You know.
Right. It's plated in vibranium.
Yeah.
Absolutely. So unfortunately, the math of the heat problem was not revealed. I do reviled. Yeah. I don't like. I still don't understand the title. And I did though revile his math. Like that's fair.
I'm coming away with this with more questions than I came in.
Yeah, no, I'm coming away with it. That's just like because I mean, you've obviously done a lot of work, but like you can get to this is a problem with the back of the napkin calculation, right? Like, present. So to do this video right, because let's the teacher in me is gonna come out for a second. To do this right, the video that I would want to see where we could actually like engage with it on a science level, right, would be one, like state the problem, right? So hey, and like state the problem accurately, right? So we need to see them do that. And then we would need to see, okay, so then this is sorry, I need to give yes, Scott, I'll give you a wrench. Just give me a second. And I need to do that. I'm sorry.
You'd have to state the problem.
Yes.
How much heat? What is the problem we're trying to solve? and then you have to propose a mechanism and show all of your assumptions, like because your model's going to have assumptions. Every model has them.
Yeah.
You need to state your assumptions, and then you need to show all of your work and show why you can keep the temperature at the surface where NOAA is at a livable temperature the entire time. It's not good enough to say that, oh, we're going to melt the crust, but it'll be fine in 3 years. Well, that's not fast enough for NOAA, you know?
Right. Thank you. That's so that's what we need to do. And like, listen, I'm not going to freak out if like you're off by an order of like, what's an order of magnitude between friends, right? Like get to the heat problem within like a factor of 10 and we can talk, right?
Yeah. Yeah, if they got within one order of magnitude of solving the heat problem, that would really that would shock me.
That would shock me. That would be amazing. Yeah. I just need to know how NOAA survived, right? And if you want to claim a miracle, that's fine, right? Like you're certainly allowed to do that, but then don't be upset that like that's not a good enough answer for me.
At that point, you're not doing science,
right?
You've abandoned evidence. Evidence doesn't matter.
Right.
Because you're just going to say that it's magic effectively, which again,
right.
That's what you want to do, fine.
Yeah. But like recognize then that can't be demonstrated scientifically. Like magic is outside the realm of science. And then I would postulate that like if your theology can be, or like your like worldview, what you believe is boiled down to like I could replace God with Gandalf, right? Like maybe.
So on the one hand, I do give props to people like Baumgartner who are at least honest. And like, I need magic for my model to work. Like, you have Gandalf in the sky or whatever. You have a source of magic, so I guess use him. You know, at least that's honest. But yeah, it's not rigorous at that point.
It's certainly not rigorous. And then like,
it's also it always strikes me as deceptive because like as who was it that said I refuse to believe that the creator who gave me a mind intended me to forego its use was like Galileo. Like
maybe, but that's my new favorite quote. Like
if all of the evidence points to A, wouldn't it be lying or deceptive for God to magic things so that it looks like A, but it's actually B? You know, like
right. I think that presents a lot of theological problems. But like those aren't mine to wrestle with because that's not what I believe. So yeah.
Well, that was the thing.
Anyway, well, thank you so much for coming on. I'm going to let you go. I know you got very important things to do.
Yeah, got to save the multiverse.
Hopefully it has to do with Dungeons and or Dragons, right? You got to get through those, slay a dragon. So to wrap up, do you have anything that you would like to shill or anything coming up?
Sure. I just released our podcast on critical race theory, which has been in the news lately. So if you want to know if critical race theory is going to like indoctrinate your kids or like destroy the nation or something, you can go check that out. All the links are in the description. We do general skepticism once a month, and then we do something religious once a month. So if you're interested in skepticism, you might like it.
That's awesome. I just got a new book on some of the very basics of critical race theory. I'm very excited to read some of it and, to do my own research by reading academic works.
You don't do your research on Facebook?
No. So that's awesome. And guys, the link to that is in the description. You're getting a video from me tomorrow, team. If I can finish editing this IPCC report video, I'm going to try to get it out tomorrow. So we can talk about latest UN report on climate change. But if not, it'll be on reading weather station. No, backing and veering. That's the next in Weather 101. One of those is coming out tomorrow. We'll see. So with that, I'm going to let you guys go for the evening. Thank you so much for hanging out. I'll see you next Wednesday, team. Okay, good night.